Okay, we stopped here last time. We're still talking about chapter 14, which is metal forming. We stopped here last time about the material behavior in metal forming. Material behavior in metal forming, right? So, actually, we said metal forming as we described last time. We deform the material, no cutting, starting volume, volume is constant, all time volume is constant. You do material deformation. So we know that if you have a bar like this one from earlier, previous study, if you have a bar like this, you're subject to tensile stress. If you have a bar like this one have a tensile stress. When you apply tensile stress for this one, what will happen? It will be elongation will happen. It will be longer, right? So you see that this one initially, this is the initial length, but when you apply tensile stress become longer. So stress applied here equal to F divided by A. We said that sigma equal to F divided by A, or AO, F divided by AO, and AO here is the original area, the surface area or cross section area. So sigma equal to F divided by AO, and E equal to epsilon equal to L minus LO, final L minus LO divided by LO. This is the strain. This is the sigma and strain, and usually we have a curve. Stress strain diagram. This is a stress, this is strain, and this is stress strain diagram, and this is a yield point. After yield point, this one will be start to elongation, permanent deformation. After yield stress, this one will be permanent. This what we call is the engineering stress and engineering strain. This we call it as this two. We call it as a engineering stress and engineering stress. As this one we cannot use actually in metal deformation. This one can be used only in linear deformation. In the design. In the design level, if you do design, you don't want, in the case, what is the difference in the design? You don't want to exceed the yield point. This is the yield point, right? In the design level, we don't want to exceed the yield point. We are working in an elastic limit. If you working in elastic limit, this equation probably okay. These two equations probably okay if you working in elastic limit. However, in metal forming, we exceeding yield stress. This is a yield point. We exceeding the yield stress. As long as you exceeding yield stress, what will happen? You deform the material. Material will be permanently deformed. So elastic region here, material will recover. Then this one should be okay. But in metal forming, when you exceed the yield point, this kind of equation, engineering stress and engineering strain, will not be valid anymore. We cannot use engineering stress and so what to use actually? Stress actually equal to actual F divided by actual area. Because you see that after material deform, what will happen? After permanent deformation, material will be longer. Volume is constant and length is increased. So from where the volume will be compensated? As long as the volume constant, length increase mean diameter is getting smaller. You see that area is not AO. We said here sigma equal to F divided by AO. AO is the initial area, the cross section area, but this one not exist anymore. Area is not same as AO because material here permanently deformed. Then stress here equal to actual F divided by actual area, which is not AO. This whatever we call is a true stress in metal forming, and there are also true strain. Cannot be simply said that L minus LO divided by LO because LO is not exist anymore because the material deformed, so permanently deformed. When you release actually, you will not get LO anymore. There will be no LO. Then strain must be obtained as an integration from LO to L, from LO initial length to final length, delta L divided by L, which when you do the integration, it will be equal to ln L divided by LO. This whatever we call true strain, and this is a true stress. Actually, this is the curve that we have. Actually, sorry, this is the equation that we have later on in the metal forming. So metal forming, in very simple way, we cannot use engineering stress, engineering strain anymore, but in material deformation, we're going to use whatever we call true stress and true strain. If you have any question anytime, you can stop me, right? Here in this slide, he trying to obtain the relation between true stress and true engineering stress and true stress. This is a true strain. This is a true strain equal to ln L divided by LO. Meaning ln LO, L equal to LO plus delta L divided by LO. This means equal to ln 1. This is 1 plus delta L divided by LO. It means that this one is engineering strain, meaning ln 1 plus E. Here, try to give you comparison. The idea here is just only to give you comparison to show you what is how they are different. I mean, the engineering stress and true engineering strain and true strain, how they are different. If you, this is for a small deformation. When you come to the small deformation, you can see here small deformation almost same engineering stress and true engineering strain and true strain are almost same if you have a small deformation. But when you have a larger deformation, if you have a bigger deformation, you see that it is, they are different, not same actually. You can see that. Then you can see that if you have a big deformation, then here this is the engineering strain is equal 10, the true strain equal to 2.4. So true strain, they are, you can see that they are totally different. So you can see that for a small deformation, in the elastic limit, small deformation mean in the elastic limit, almost in elastic limit, okay, you can use either this one or that one. So simply in the elastic deformation, in a very simple way, is using the engineering strain. But in a big deformation or larger deformation, you must, listen to me carefully, you must use that true strain and not engineering strain anymore. For circle cross section, epsilon equal to ln divided by LO equal to ln, it's corresponding to ln AO divided by A or ln DO square, the DO divided by D square, or 2 ln, because this is 2 become 2 ln DO divided by D. This is for circular cross section, for circular cross section. Also here trying to obtain a relation between sigma and S. S is engineering stress, sigma is the true stress. Sigma is the true stress, which is equal to F divided by A. Then F divided A multiplied by AO divided by AO. This is simply one. Just try to show you the difference. Then F divided by AO multiplied by AO divided by A. Then this one equal to F divided by AO equal to S, which is the engineering stress multiplied by AO divided by A, or L divided by LO. Then you can see that there are a difference. They are not same. They are not same. So this is a relation between engineering stress and true stress and engineering strain and true strain, and this is the relation between. So now from now in the, when you say that in a material, in a metal deformation, we're not going to use engineering stress and engineering strain anymore, but we're going to use true stress and true strain, right? This is a true stress true strain relationship. This is a stress strain curve. You know that, stress strain curve, you know that previously. This is not first time, but now the new that this one is a true stress true strain curve. This is not engineering stress engineering strain, but true stress true strain curve. The between stress sigma and epsilon is this curve. It is shown here, and this relation could be described as sigma equal to K epsilon N. K epsilon N. This is fitting. When you do square fitting, we can describe this relation. Stress strain diagram previously, sigma equal to E epsilon, now K epsilon N. now equal to K epsilon N. K, we call it as a strength coefficient. K, we call it as strength coefficient. And K is a true stress corresponding to epsilon equal to 1. Then epsilon equal to 1, at epsilon equal to 1 here, epsilon equal to 1 you got here like this, and then you obtain the stress value. So K, this one, this is a K, let me highlight. This is a K. What is a K? K, we call it is the stress coefficient, and K equal to the true stress value corresponding to epsilon equal to 1. Epsilon equal to 1. This is a K. Epsilon is a true strain, and N here we call it is a strain hardening exponent. N we call it is a strain hardening exponent. Strain hardening exponent. And this N can be obtained as a slope of the curve in log-log scale. So this is a curve actually. This is a curve in log-log scale. This one become linear curve in log-log scale. And N here is the slope of the curve log-log scale. So this is the N, which is the strain hardening exponent. K and N are constant for same material. K and N are almost constant for same material. However, this curve, if you see this curve, which is sigma equal to K epsilon N, in general, this one describes the curve from beginning, from 0 to fraction. Then sigma equal to K epsilon N. However, in a material deformation, in metal deformation, we are concerning about material after yield point. We are concerning about the material after yield point here, this range. So we are concerning about material after yield point. Material below yield point we are not concerning about. Why? Why we are not concerning about material below yield stress? Because material below yield stress is material, no deformation happen. Below yield stress, no deformation, no permanent deformation happen. Permanent deformation happen after exceeding yield point. So in metal forming, we are concerning about the material after yield point. So we consider is this kind of blue curve. Can you see that? We are concerning about this blue curve. We call it is flow curve. This blue curve, we call it is the flow curve. It is part of the curve. It is part here from after yield point. This blue curve, we call it flow curve. We call it flow curve. So YF is sigma, we consider as YF, which is, now we change sigma to YF. The word YF mean flow stress. YF is the flow stress. Here in this blue curve, YF is a flow stress equal to K epsilon N. Not sigma anymore, but YF. It is same. This equation is same. Then sigma replaced with YF, and here we call it is a flow curve. So flow curve actually is a true stress, true strain curve after yield point. We are concerning about this area because this area is deformation happen, right? So K is strength coefficient and epsilon is a true strain, and N here strain hardening exponent we can obtain from the slope of the line in the log-log scale. Actually, when you come to the N can take value between 1 and 0. If N equal to 0, this is the horizontal line. If the slope is 0, then this is a horizontal line. What does that mean? It means that material is rigid. We call it fully plastic material. This does not exist. We don't have this. We don't have whatever we call is a fully plastic material and rigid. It's a theoretical case. It means that if you apply stress, and you exceed, nothing will happen. And then when you reach to the yield stress, material will deform plastically without any elastic deformation. So if n equal to 0, it means that you increase the stress, nothing will happen. But when you reach yield stress, material start to deform at constant load, permanently at constant load, and no elastic at all. We call it rigid. So a material here, in case of n equal to 0, it's rigid, and we call it fully plastic material. And if n equal to 1, it means that material is ever elastic, always elastic, and no deformation. Also, this is one very theoretical. So n here is 1. This is n equal to 1. If the slope equal to 1, it means that like this. This slope equal to 1, and a slope equal to 1, it means that it is always elastic. Whenever you apply stress, you release, you get 0. When you apply stress and release, get 0, and so on. Then the material is always elastic. N is between 0 and 1. Actually, n have value between 0 and 1, not 1 and not 0. This 1 and 0 is usually theoretical case to show you what is the limit of n, but n usually in actual is between 0 and 1. Then you can see here, this is the case, for example, this one elastic, fully elastic or perfectly elastic. We don't have this. This one perfectly plastic material, or we call it rigid or perfectly plastic. But actually, this is the case. Actually, this is the case. Material, elastic plastic material. Elastic plastic material. Material always is elastic plastic. So in this case is elastic and then elastic plastic material. This is the case always we have, or actual case for material in the being used regularly. Okay, this is a flow curve where K epsilon equal to sigma equal to K epsilon n. This is the equation of the curve. This is a flow curve, right? Okay, so the work usually is the area under the curve represent whatever we call is the unit work or a specific work. This is the stress equal to what? Stress equal to, if you look to stress equal to force divided by area, which is a Newton divided by meter square. This is a stress, right? Strain equal to no dimension. Strain here is a no dimension. Stress here can be written as Newton meter divided by cubic meter. Newton meter by cubic meter. Newton meter by cubic meter mean joule per cubic meter. Stress can be written as, let me write, stress can be written as Newton meter divided by cubic meter. So Newton divided by meter square, which is a stress, also can be written as Newton meter divided by cubic meter. Newton meter is a joule, is a work actually. Newton meter is a work. So it is joule per cubic meter. Joule per cubic meter. So Newton meter per cubic meter, which is joule per cubic meter. Joule, this is the work. Nm is or force multiplied by distance. I mean, force multiplied by distance is a work. So work divided by unit volume. So it is unit work. So the area under the curve here, because the strain is dimensionless, if you get the area under the curve, because this kind of stress happened due to the strain, when you increase the strain, can you see that? When you increase the strain, stress increase. When you increase the strain more, stress increase. So it happened due to the strain. Then when you get the area under the curve is joule per cubic meter. Joule per cubic meter is whatever we call unit work. Unit work because it is per unit volume. If you would like to get the volume, it is the area under the curve multiplied by volume. If you get the work, if you would like to get the work, it is the area under the curve multiplied by the volume of the material. Then U equal to what? Area under the curve. Area under the curve meaning from 0 to epsilon 1. This is the strain value. Integration from 0 to epsilon sigma d epsilon. This is the area of the element. We take element. this element we integrate from 0 to epsilon, from beginning to end. The area of the epsilon, for the area of the element equal to sigma multiplied by d epsilon. Sigma multiplied by d epsilon, this is the area of the element. Because finally we would like to get the area under the curve. To get the area under the curve, we have the element, we use the element and do integration. So this is the element, sigma multiplied by d epsilon. This is the area of the element. We will integrate from 0 to epsilon. Then sigma can be replaced by k epsilon n d epsilon from 0 to epsilon. And then do the integration. Then the area under the curve equal to k epsilon n, k epsilon power n plus 1 divided by n plus 1. This is the area under the curve. This is the unit work. So actually this is the unit work, which is equal to unit work, which is equal to a joule per cubic meter. This is the unit work. If you would like to get the work, then you can multiply this one by volume. Yeah, Muhammad, yes.
دكتور, what is this orange thing اللي تزال في الرسمة؟ ايوه وش
ده
هذا؟
element يا محمد. element. انت محتاج تعمل integration. You need to do integration. How to get the area under the curve. To get the area under the curve, you take element. This element is the area of the element is sigma. sigma الطول في العرض. مساحة الاليمنت ده طوله في عرضه هو مستطيل. الاليمنت ده شكله مستطيل صح؟ لانه صغير جدا. احنا بناخد اليمنت صغير جدا ونعمل له integration from 0 to epsilon. فالاليمنت ده مساحته كام؟ مساحته طوله في عرضه. الطول بتاعه سيجما قصدي. سيجما يعني ايه سيجما؟ سيجما يعني اي قيمه لسيجما. يعني لو انت جبت الطول بتاعه هنا اهو مدد ده كده، الطول بتاعه بيساوي ايه؟ سيجما. any value. راح صح؟ يبقى طوله سيجما في عرضه دي سيجما. فالسيجما دي مساحه الاليمنت اللي هو الاصفر ده. فانت تعمل له انتجريشن من صفر لابسلون عشان تجيب المساحه تحت الكيرف ده. Did you get it?
Thank you.
This is the area under the curve. This one which is U1 is the area under the curve. فاحنا يا شباب زي ما انا كنت بقول دلوقتي احنا عملنا الاليمنت ده بنعمل له انتجريشن من 0 لابسلون. فنجيب الاريا. This is the area under the curve which is the U1 which is represent unit work, right? So this is the unit work k epsilon n divided by n plus 1, right? However, for simplicity they said like this. For simplicity, integration and so on. For industry, they don't want to do integrations, big headache. So how to deal with this one? They simply said that, okay, listen to me carefully, guys. Please listen to me carefully. This area under the curve, the blue area under the curve, they said that equivalent to this area, which is the red in color. Can you see this area? So they said that this area will equivalent to the blue area. This area is something like rectangular area. This area is a rectangular area equivalent to. Someone said how equivalent? You can see this area is excluded, this area is included. So we include this area and we exclude this area. This one is almost equal to this one. Finally, the blue area under the curve equal to the red area here under this triangle. Then what is the area under the rectangular? What is the area under the rectangular here? Which is equal to y bar multiplied by epsilon 1. Then y bar multiplied by epsilon 1, this area. This is imaginary area. Imaginary يعني تخيلية. يعني يا شباب هي القصة عايزين نعمل ايه؟ احنا عايزين نجيب اريا سهلة بدل الاريا المكعبلة دي. يعني احنا عندنا الاريا، خلينا نرجع تاني. احنا عندنا الاريا دي اللي هي البلو اريا دي اندر كيرف. دي اريا دي ايه؟ ملهاش شكل هندسي. الاريا الاندر كيرف دي اللي هي البلو اريا دي ملهاش شكل هندسي محدد. فاحنا عشان نجيبها لازم نعمل انتجريشن. فعملنا انتجريشن فعلا وجبنا الاريا دي. الطريقه دي طريقه صعبه. احنا عايزين طريقه اسهل من كده. easy way to get the area. what to do؟ ندور على اريا تانية يكون شكلها سهل، شكلها شكل هندسي. ماشي؟ تمام؟ فين هي الاريا دي؟ اللي هي دي. مستطيل triangle سوري rectangular. this is the area مستطيل. تمام؟ شايفينها اللي لونها احمر دي؟ الاريا دي الجديده دي اريا تخيليه. اريا تخيليه ما هياش هي الاريا الثانيه. الاريا التخيليه دي احنا بنقول انها equivalent للبلو اريا. I mean the new area the red area will be equivalent للبلو اريا. how equivalent؟ هتلاقي عندك الحته دي زياده مش موجوده معانا، الحته دي برضه ما كانتش موجوده تحت البلو، فكأن دي بتساوي دي. لو انت قلت دي بتساوي دي يبقى نقول الاريا الحمراء دي بتساوي الاريا الزرقاء. طب الاريا الحمراء دي بتساوي ايه؟ بتساوي واي بار ملتبلاي باي ابسلون اهي، لانها مستطيل. واي بار اللي هي النقطه دي، واي بار اللي هي النقطه دي ملتبلاي باي ابسلون. يبقى الواي بار ملتبلاي باي ابسلون. اديني يا محمد بس دقيقه، خليني بس اقول كده وبعدين اسالني. الاريا دي الحمراء دي اللي هي واي بار ابسلون بتساوي ايه؟ بتساوي الاريا الزرقاء اللي موجوده دي، يبقى اللي هي الايه؟ اللي هي الكي ابسلون 1 كي ابسلون باور ان بلس 1 ديفايد باي ان بلس 1. يبقى الاثنين دول بيساووا بعض. طيب يبقى الواي بار دي بتساوي كام بقى؟ فين النقطه دي؟ where this point where that make the blue area equal to red area, then y bar equal to epsilon to go this other side, then y bar which we call average flow stress is equal to k epsilon n not n plus 1 لان الابسلون دي راحت مع ال1، يبقى k epsilon n divided by n plus 1. this one we call it is the average flow stress. What is the benefits of having average flow stress? Easy way dealing with this one. So average flow stress, if we just imagine, stress is constant from beginning to the end, then it will be y bar. So average flow stress is equal to y bar constant from beginning to end. Actually, this is not exist. We don't have this. We have stress increase gradually and reach to maximum at certain value. This is the actual stress, but for simplicity, we can imagine that stress start from beginning to the end as a constant equal to y bar, but finally, the area under the curve here will equal to the area under the curve as a blue curve. Y bar always smaller than yf, because yf here is the maximum here, y bar is the average. So always y bar is lower than or smaller than y flow or actual y flow at epsilon value. Yes, any question? I'm listening. Yeah, I'm listening. Is it clear what I said? I'm listening.
Yes, Doctor, clear, but I'm asking, will we always use the average flow instead of the blue
just
one?
Wait. This one, just wait. I'm going to explain about this one. I will give example and see how to deal with that. But just now, any question about what I said? If not clear, then you can ask me. Anyway, we have now. Yes, Mubarak.
يا دكتور، بالنسبة دكتور الافرج ستريس، هو القيمة حقتها تمثل الافرج بين ايش وايش بالضبط؟
انت قول لي.
بين اللي هو الفلو وبين اقل قيمة او ايش بالضبط؟ ما ادري والله صراحة ما فهمت عدل.
ما عشان ركز معايا. طيب just give me your attention guys. Again I will see again. average يا شباب يعني عايزين نخلي الاريا دي، الاريا الجديده دي للتسهيل. هي عمليه يا باشمهندس، انا بتكلم بالعربي اهو. العمليه دي للتسهيل. انت اصلا عندك، ارجع تاني، انت عندك الاريا دي اللي هي البلو اريا اللي هي الاندر كيرف دي. البلو اريا دي شكلها ملهاش شكل هندسي سهل. عشان تجيب الاريا البلو اريا دي لازم تعمل انتجريشن. تمام؟ ودينا عملنا انتجريشن فعلا. في الصناعه يعني عمليه انك تعمل انتجريشن والعمليه شكل الكيرف يعني ما هوش دي شكل هندسي محدد، يعني المهندسين بيبقوا عايزين عمليه اسهل من كده. فنعمل ايه؟ تخيلنا ان الاريا دي، الاريا اللي هي البلو اريا دي، جبنا اريا ثانيه ايكويفالنت ليها. ايكويفالنت يعني بتساويها يا باشمهندسين. فاحنا قلنا الاريا الحمراء دي اريا ليها شكل هندسي محدد، اللي هي عباره عن ايه؟ مستطيله اهي قدامكم اهي، ليها شكل هندسي محدد. الاريا الحمراء دي بتكافئ الاريا الزرقاء. يعني ايه بتكافئ؟ يعني بتساويها. تمام. طب الاريا الزرقاء احنا جبناها اوريدي، الاريا الزرقاء احنا جبناها من الانتجريشن اهي، دي مساحه الحته الزرقاء دي احنا جبناها من الانتجريشن اهي. طب الحته الحمراء دي بتساوي ايه؟ بتساوي الواي بار ملتبلايد باي ابسلون، اللي يعني احنا سميناها الافريج ستريس. يعني الواي بار هي اسمها الواي بار كده، واي بار افريج. ليه سميناها افريج؟ لان الاستريس بيبتدي كونستانت فاليو من البدايه للنهايه عند سيم فاليو which is actually not exist. يعني الحقيقه ان الاستريس بيزيد جرادولي لغايه ما يوصل للماكسيمم، لكن احنا imaginarily تخيلنا ان احنا لو خلينا الاستريس ثابت من البدايه للنهايه سميناه الافريج ستريس، هتبقى الاريا دي فاينلي الحمراء equivalent للاريا الزرقاء. فاحنا لما سوينا الاريا الحمراء اللي هي الواي بار فلو ملتبلاي باي ابسلون، لما سويناها بالاريا الزرقاء لقينا ان الواي بار كان بي اوبتيند از من هنا اهو، ان الابسلون دي لما احنا سويناها الابسلون دي تروح مع الواحد اللي فوق ده، يبقى الواي بار بتساوي كي ابسلون ان ديفايدد باي ان بلس 1. دي اللي هي الافريج ستريس، سميناها الافريج ستريس. ليه سميناها افريج ستريس او افريج فلو ستريس؟ لان الفلو او الاستريس بادئ كونستانت من البدايه للنهايه، عشان كده سميناها افريج ستريس. ذاتس ات. مبارك؟
اي وضحت دكتور.
تمام. ذاتس ات. طيب دي الايديا. يبقى ده الفلو ستريس، ده الفلو ستريس العادي كي ابسلون ان بلس 1 ديفايد باي ان بلس 1. دي الفلو ستريس عادي ات اني بوينت. لكن دي الافريج فلو ستريس. How to deal with both? How to deal with these two cases? Let's take an example. The annealed alloy steel tensile test specimen دي اللي قدامكم دي with gauge length 100. gauge length يا جماعه يعني طولها كان 100 قبل ما نعمل اي حاجه. gauge length يعني original length 100 is stretched to 150. يعني هي it was 100 millimeter. It was initially 100 millimeter. After we applied tensile stress, it is elongated to 150. Then final length is 150 millimeter. Annealed alloy steel has a flow curve with a strength coefficient 700. This is a strength coefficient K. He said that flow curve with a strength coefficient 700 megapascal. This is K, and strain hardening exponent with N. So this is the K and N. This is the value of K and N for this material, which is given. Determine the flow stress and the average flow stress. We need to obtain what is the flow stress and what is the average flow stress. Okay, what is the flow stress? خليك معايا يا باشمهندسين لو سمحت. Please give me your attention. لو سمحت ركز معايا. Please give me your attention. البار ده يا جماعه خلينا نتكلم بالعربي. البار ده اتشد من 100 ل 150. من كام؟ من 100 ل 150. يعني طوله النهائي بقى كام؟ 150 مللي. هو كان كام؟ 100 بقى 100 وكام؟ 150. يبقى الاسترين بيساوي كام يا باشمهندسين؟ الاسترين ما ترو سترين بقى، ما تقوليش دلتا ال على ال، خلاص ما عادش ينفع دلتا ال على ال، ما بنستعملش مع دلتا ال على ال. دلتا ال على ال دي بنستعملها في حاله الديزاين لما بنكون في الالاستيك ريجون. لما نتكلم في البلاستيك ريجون ونتكلم على البيرمنت ديفورميشن ما ينفعش نقول دلتا ال على ال تاني. نقول ايه بقى؟ بنقول لن ال ديفايدد باي ال او. لن ال ديفايدد باي ال او. ال بكام يا جماعه؟ 150. ال او بكام؟ ب 100. يبقى الاسترين بتاعي كام؟ 0.405. ده الاسترين. عند كام الاسترين ده يا جماعه؟ الاسترين ده عند 150 مللي. يبقى نقول اهو الاسترين اهو. يبقى كأن الكيرف ده الاسترين عندي، ده الفاليو بتاع الاسترين اللي هو كام؟ ركز معايا بقى. الاسترين اللي هو كام؟ 0.405. يبقى دي قيمة الاسترين يا باشمهندسين. يبقى عندي الاسترين بيساوي 0.405. الاستريس كان بيساوي كام يا شباب؟ ده السؤال. يبقى عايزين نعرف الفلو ستريس. يبقى الفلو ستريس ايكوال تو كي ابسلون ان. عند السترين ده اللي هو 0.405 الاستريس بيساوي كي ابسلون ان. كي اند ان ار جيفن، هو مديهم لي، فانا نعوض في المعادله يبقى الاستريس بيساوي كي اتش از جيفن ابسلون 0.405 باور ان، يبقى ده قيمه الاستريس 611 ميجا باسكال. ده معناه ايه يا شباب؟ خليك معايا الله يكرمك، give me your attention please. ده معناه ايه؟ معناه عشان تعمل الماتيريال دي، تشد الماتيريال دي لغايه عشان توصل ل 150 ملم، انت محتاج تعمل ستريس توصل لستريس قيمته المفروض تزيد 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 لغايه ما توصل 611. لما توصل 611 ميجا باسكال الديفورميشن عندك هيبقى 150 ملم. ده معناه فلو ستريس. كلمه فلو ستريس معناها الاستريس يو نيد تو فلو ذا ماتيريال. كلمه فلو ستريس معناها الاستريس يو نيد تو ابلاي تو فلو ذا ماتيريال. يبقى انت عايز تزود الاستريس، تزود 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 تزود. هنا عرفنا ان لما توصل 611 ميجا باسكال يبقى وصلت للطول المطلوب اللي هو ال 150 ملم. طب انا هسألك سؤال تاني، لو احنا عايزين نوصل ل 200 ملي يبقى الاستريس بيساوي كام؟ يبقى احسب الاسترين المناظر يبقى بيساوي كام؟ لن 200 على 100، يبقى جبنا الاسترين جديد. فين هو؟ اهو، يبقى ده الاسترين الجديد. تروح طالع كده ماشي، يبقى نيو سترين. فين الاستريس؟ اهو الاستريس اهو، انذر ستريس انذر ستريس. يبقى انت لو عايز توصل ل 200 مثلا فور اكزامبل يبقى 650، يبقى تزيد 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 لغايه ما توصل 650. لما توصل 650 هتوصل للجيج لينس بيساوي كام؟ او لللينس الونجيشن بيساوي 200 ملم. دي ريليشن بين الفلو ستريس اند سترين. يبقى الاسترين يا شباب هو عند نقطه محدده. الاسترين عند نقطه محدده. قال لك 150 مللي يبقى انت بتجيب الاسترين عند 150 مللي. قال لك 200 مللي يبقى انت بتجيب الاسترين عند 200 مللي. بتجيب الاسترس المناظر ليه؟ يعني ايه الاسترس المناظر ليه؟ يعني قد ايه ستريس I need to apply to reach to this length. واضح يا شباب؟ السؤال الثاني ايه الافريج فلو ستريس؟ الافريج فلو ستريس يا جماعه بيساوي ايه؟ يبقى واي بار بيساوي كي ابسلون ان على ان ديفايدد باي 1. when we applied لقينا الافريج فلو ستريس في الحاله بتاعتنا بيساوي 532. معناها كلمه الافريج فلو ستريس، الله يكرمك اسمعني give me your attention please، معناها انك انت لو تخيلت ان الاستريس بتاعك كونستانت، معناها ان انت لو تخيلت الاستريس بتاعك كونستانت بادئ من البدايه للنهايه at same value. الاستريس بتاعك كونستانت من البدايه للنهايه at same value there are no change. يعني يبدا الاستريس بتاعي كونستانت من اول لحظه لغايه اخر لحظه عشان يوصل للاسترين اللي قيمته 150 او بيناظر 150 ملم، هيكون الاستريس بتاعي 532 ميجا باسكال. يبقى الواي افريج بتاعتي 532 ميجا باسكال. دي الواي افريج اللي هي الافريج ستريس من البدايه للنهايه اللي يحقق لي لينس ايكوال 250 ملم. واحد هيجي يقول لي ما عنديش كلام من ده، انا ما عنديش ستريس كونستانت. انا عارف يا سيدي، انا عارف. we know we don't have constant stress from beginning to the end. Stress increase gradually and reach to the maximum stress. انا فاهم، بس الكلام ده عملوه علشان يبقى عندنا area under the curve with certain easy shape. I mean engineering shape like rectangular shape. خلاص سميناها الافريج. يبقى تخيل just imagine يبقى الافريج flow stress equal to k epsilon n divided by n plus 1. When you apply then you get average flow stress as if you start from beginning to the end with the same stress without any change which is not exist. اي سؤال يا شباب؟ اي سؤال يا باشمهندسين؟ any question guys؟ Clear? Did you get it? Okay, that's it. Another example, determine the value of strain hardening exponent. What is a strain hardening? Strain hardening exponent يا جماعة اللي هي N for a metal that will cause average flow stress to be 80% of the final flow stress. Always يا شباب خلي بالكم يا باشمهندسين معايا، دايما الافريج فلو اقل. You agree with me ها؟ لازم، مش ممكن يكون اكبر يعني ها؟ عمره ما هيبقى اكبر من الاكتوال فلو ستريس. ده الفلو ستريس وده الافريج فلو ستريس. He said read together determine the value of strain hardening exponent for a metal that cause the average flow stress اللي هو الواي بار will be 80%. الواي بار will be 80% of the flow stress which will YF. Then Y bar flow equal to 80% of Y flow. What is the strain hardening exponent? Put the equation. Y bar flow equal to K epsilon N divided by N plus 1. Y flow equal to K epsilon N. Then you can see here in this equation, K epsilon N, go with K epsilon N, right? Then you get one equation as a function of N1 divided by 1 plus N equal to 80% or 0.8. Then it is one equation, then you get the one equation, then you solve the one equation, you get N value equal to 0.25. This is the strain hardening exponent that cause 80%. Y bar flow equal to 80% of Y flow. Okay, that's it. Temperature in metal forming. Actually, temperature in metal forming is significantly affecting metal forming. Because you know that when temperature increase, what will happen? Material becomes soft in very simple way. When temperature increase, material becomes soft. This is a higher temperature. In this direction, higher temperature, meaning that modulus of elasticity decrease, yield stress decrease, ultimate tensile decrease, strain hardening exponent N decrease, case stress coefficient will decrease, ductility will increase, toughness will increase. You agree with me, right? This is a temperature effect. In a temperature, you know that we have three range: cold range, warm range, hot range. Cold meaning less than 0.3, warm is between 0.3 and 0.5 melting temperature, and hot between more than actually 0.5 and less than 0.75, and no melting. Always here in metal forming, no melting, guys. If you melt, it will be casting. So no melting at all. We have no melting. We have only heating, right? So up to 0.75. This is three range. So the question is, which one is better, cold, warm, hot? Shall we work with hot because temperature is good? Then when we're heating and up to hot is fine, then easy to deform the material and so on. I tell you that every case have some advantages and some disadvantages. And in this section, let's try to see what is the advantages and what is the disadvantage, and then let's get a conclusion, have a conclusion from this section to see whether it is better to have a cold working or warm working or hot working, or how we can deal with the metal deformation regarding to the temperature, right? Start with the cold working. Actually, cold working, it could be at room temperature, could be a little bit heated, but less than 0.3 melting temperature. Don't exceed 0.3 melting temperature. As long as it is less than 0.3, it is considered as a cold working. Even it may be heated, but considered also as a cold working. So performed room temperature slightly higher, and many cold working processes are important in a mass production, and no machining required, and operation knit shape or near knit shape. What does that mean? It means that there are a very important benefits we get when we having or when we're doing cold work. What is that? Geometrical accuracy is excellent in cold working. Why? Because no heating. What happens in heating? When you heat the material expands, and later on you do deformation while material in expansion condition. And later on material contract. When material contracts, then all geometry is changed. يعني يا شباب بالعربي احنا بنسخن الماتيريال. لو انت شغال هوت ووركينج بتسخن الماتيريال. لما انت بتسخن الماتيريال بتتمدد، انت بتعمل ديفورميشن والماتيريال في حاله تمدد. A later on material will cool down. After deformation material will cool down, a material shrink يعني بتنكمش. when material shrink all geometry will change. This is big issue. Then geometrical accuracy actually in cold working is excellent. Why? Because we no need to heat, no expansion and no contraction. So in cold working, if you deform the material in cold working, this is a final deformation. Material will be deformed finally and almost no more contraction. Then this one leading to what? Leading to higher accuracy or material accuracy or geometrical accuracy is better in case of cold work. This is very important. That's why they call it is no machining required, and the material produced by cold working is considered as a net chip. Net chip meaning final. No need to do machining. No need to do machining because geometrical accuracy is in somehow very good. This is a benefit, very good benefits. Advantages is better accuracy. We can just conclude that advantage of cold working is a better accuracy, closer tolerance, better surface finish, strain hardening increase. Strain hardening increase because the material deformed here. You can see that when you deform the material in cold working, grain here will deform it. This is the grain here. You're squeezing the material between the two rollers, for example. Then what will happen? Material grain will distortion and will deformed. As you can see, this one will leading to high whatever called strength hardening. Strain hardening and strength hardening will increase. There will be residual stress, very high residual stress here, including make the hardness or strain hardening. Strain hardening of the material will increase, and grain flow direction can be caused desirable direction flow. Material will flow in desirable direction. It depends on what is actually needed. And no heating is required. This is the advantages of the cold working, right? What is the disadvantages? What is the disadvantage of the cold working? The disadvantage is a higher force and power required. Yes, because material is not soft, then you need a higher force and you need higher power. You need to clean the surface, totally clean the surface. Ductility, strain, limit the deformation. Limit the deformation, it means that if you need to do certain deformation, probably you need several stages. You cannot just do in one stage because the ductility is low. You cannot do the deformation. If you need to do big deformation, you cannot do at once. Probably you need to do one stage and then go to another stage and later go to another stage and so on. And some cases you need to do annealing in between. You need to do annealing in between to release because if you do residual stress and then you do another residual stress. So for example, if you here doing one in the cold working, doing one residual stress against this one, and then you take this one, input for second case, you do more residual stress and then another residual stress, this one leading to cracks and initiating cracks, and this one is not good for a material. Then what to do? Probably you need to do heating. Heating here, I mean, whatever we call is some cases you need to do, it depends on the material actually, you need to do whatever we call heat treatment to release some stress here, then you can you will be able to go to for next cycle. This is disadvantages. And also in other cases, in some other cases like brittle material, there's no way to do cold working, no way actually. In case of brittle material, very hard material and brittle material, there will be no way actually to do cold working. You must do hot working. So it will be very difficult to do cold working in a brittle material. This is the disadvantages. This is the advantage and this is the disadvantage. If you come to the warm working, you find that warm working something between the hot working and cold working. So I have a good as the compromise in warm working, it is between 0.3 and 0.5 melting temperature. Advantage is a lower force than cold working because you heat the material a little bit heat up to 0.5. Then lower force and lower power and more material, geometry material is still no material distortion. Materially is originated and no annealing probably will need between the cycle. No need for annealing because here you increase the temperature up to 0.5, then You get good benefits in case of warm working still. What is the disadvantage? Disadvantage is that you must heat the material. Heat the material, it means that you need to pay money to heat the material. Because heating the material, you need a furnace, you need to pay money for heating the material. We consider as a disadvantage. Next is hot working. Actually, time is finished. I have to stop here. Let me stop recording.